Hello class, for this morning's lesson we're going to be looking at the measuring center and spread of a binomial probability distribution, and we're going to look at some problems where we're going to have to solve for the number of trials needed for some given conditions. They're interesting problems, but they're mostly CAS techniques, so we must have our CAS available for this. We need to be able to calculate the mean and variance. Okay, and the ways of calculating standard deviation and median and mode, they all follow on from a standard discrete random variable approach to calculating those quantities. Okay, let's get to it. We're going to start with an exam problem. Please note these are the exercises that you need to be doing today. Okay, let's get right to it. So this is from past exam, in exam 1. So there's no CAS allowed and no notes. So there's some things that you need to know and be able to remember to work on such a problem. So let's go through it. It is known that 50% of customers who enter a restaurant order a cup of coffee. If 4 customers enter the restaurant, what is the probability that more than 2 of these customers order coffee? Assume that what any customer orders is independent of what any other customer orders. So that last bit is quite crucial because it is essentially giving us a clue about what kind of probability distribution this scenario will follow. Because the term independence here is referring to the customer, which in this case is like the number of trials and the probability of the outcomes between number of trials. And that is quite characteristic of a binomial distribution. So the first step is to be able to identify that we've got some random variable x, that is binomial distribution random variable, and we have a probability of an outcome, which in this case 50% of customers who enter a restaurant order a cup of coffee. And we've got number of trials, in this case 4 customers. And first identifying that information allows me to set up my probability problem. Now, what do I know about a binomial distribution? Well, the probability of the random variable having some value x is given by this rule. Now I need to be able to have some understanding of what that rule looks like and where numbers go in each part. So a little bit of memorizing this is very important. Now, what does the question actually ask me to find? What is the probability that more than 2 of these customers order coffee? Well, that's like finding what is the probability that x is more than 2 or greater than 2. Well, because it's an inequality, I'm going to be using the binomial CDF. But first, because it's an exam, I might have to be able to show some working out for my 2 marks. So up to n equals 4, I've got 2 possibilities. That is more than 2 when x is 3 plus when x is 4. Then using those 2 rules, I'm going to set that up in according to the rule here for my different values of x and n. So for n is 4, the number of trials is 4. First of when x is a value of 3, I've got probability of success to the power of x multiplied by probability of a failure to the power of n minus x. In this case 4 minus 3. Plus, and do the same for this expression, for x is 4. Okay, so having set that up, I need to start evaluating. I've got these things, the combinations. Now, being able to understand about combinations, I need to remember this a little bit. This is the expression for combinations using factorials. And remember what factorials does? Factorials takes a number and it multiplies all the numbers below it. So the factorial of 4 is 4 times 3 times 2 times 1. And then the factorial of x, which is 3, will be 3 times 2 times 1. Now n minus x is 4 minus 3, gives you 1. So the factorial of 1 is just 1. And that simplifies nicely to 4. And I can see it simplifies nicely because I can cancel out some common factors, a bit like that. They all cancel out nicely, and I just get a factor of 4 divide 1, which is just 1. The same thinking can be applied to the combination of 4 out of 4. Okay, so I'm going to take those values and plug them in there and there in my rule. And I end up with a lot simpler expression. Because it's 0.5, really I've got the same base number and I can now just add the exponents. So I'll have 0.5, which is the same as a half to the power of 4, plus, again, add the exponents. 4 plus 0 gives me just the power of 4, so a half to the power of 4. And I look at that expression, I say, same base number again. I've got 4 lots here and then plus 1 lot there, so I've got 5. 5 out of 16 as my result. And I need to be able to do that in my head. So it's important to realize that 2 to the power of 4 is equal to 16. And if I don't know that, and if I can't work that out by this stage, then I'm in big trouble. So let's have a look at what some of the things that the assessor said about this. Well, first, only 0.8 was the average mark. About half of the state got that wrong. Bit disappointing. So in other words, the assessors want you to see that you know and understand this rule. And they want you to know and understand this expression, this rule, and how to use it. So a little bit of study to do, obviously. That means you must do your homework. So setting it up like this, like the way we did it to get 5 out of 16. Students generally either attempted to use binomial distribution or a tree diagram to answer the question. Some were unable to evaluate a half to the power of 4. That's poor. Or the binomial coefficients, that are these ones. Able to work out this expression is important. Students should know that n combinations of n is equal to 1 and n combinations of n minus 1 is equal to n. There's some common facts that it's important to know and understand, and if you don't know and understand or can't remember them, then just being able to go through the processes and arrive at the answer is good enough. Okay, notation was poor and often made it difficult to ascertain if the student really understood what was required. Probably they didn't. 46% got it wrong. Common responses were 0.5 squared plus 0.5 to the power 3 plus 0.5 to the power 4. All combinations of such and incomplete tree diagrams. Probabilities greater than 1 were also seen. Okay. So there you go, that's an important thing regarding binomial distribution, and please expect questions like that on your first exam, so make sure you practice. Let's consider what's on the formula sheet of the exam. So measurement, calculus, come down to the probability section, and as we can see, looking around for something regarding binomial distribution and you're not going to get it. So in other words, you must remember. Okay, let's actually have a look at this binomial distribution. What does it look like? So, trusty Kaz. Here we go. So here's our rule, and here's our distribution plot, and I've produced this for a series of x values. I've produced the binomial distribution using this rule up in the column formula here. And I've done a scatter plot of the binomial versus x variables, and as I change my variables, so let's start low, maybe n equals 5, and as I change my probability from 0.7 down to 0.5, 0.4, 0.3, you can see the general trend on how that changes for different values of x. Being discrete numbers, 0, 1, 2, 3, and so on. Let's increase the value of n and see what happens, what it looks like now with larger number of trials. Ooh, that looks pretty. And I get a nice little wave occurring. Isn't that nice? Okay, besides all that, it's showing this kind of curved shape. As for n equals small, for p is equal to small, the probability of success is about 10%, then I get my peak at low values of x. But as the probability of success goes up to 90%, then I get my peak for high values of x. And as I increase my number of n, essentially what I'm doing, I'm getting more data points into the calculations. So I get more values and I get this much nicer and tighter curve. But binomial distributions for discrete values, so it goes 1, 2, 3, 5 and so on, or nothing in between, just those points is important to realize. So given that, let's hide that connecting line. That's better. Okay. Let's go with that. There it is. Now, why is that helpful? Well, I can find some things about it now. For instance, I might want to know a little bit about the measure of center of my binomial distribution and spread. And I can see, well, a bit of a trend here in the middle. This is like an expectation value right there. This is the mean, being the peak of my probability. So how do I get here for these parameters? N equals 50 and p equals 0.5. Why does my mean of x is 25? Well, what about if I go half of 50? That might be 25. And in fact, that kind of thinking is correct for mean, because I get these rules for the binomial random variable. The mean or expected value of the binomial random variable x is n times p, and the variance is n times p times the 1 minus p, which is your probability of a failure. Interesting formulas. And from that, of course, we can get other things like the standard deviation, which would be the square root of all this. So, record those rules, very important. Let's see how we use those rules. And generally, pretty simple rules. You just times a couple of numbers together. So it's never going to be that simple. This is more likely how mean and variance is likely to be used in a problem. Binomial random variable has a mean of 12 and a variance of 9. Find the parameters n and p, and hence find the probability. Alright, so how does that work? Let's have a look. I get all this work. Now, start off with recording what I've worked out. The mean is 12 and our variance is 9. Then I plug in my rules. NP is equal to 12. NP times 1 minus p is 9. Now, since this is known, then that becomes that. I just replace the NP there in my variance rule with information about the mean, 12. And I can now solve for p, the probability of a success. Becomes a quarter. Now once I found probability of p, how do I get n? Well, I can plug it back into one of the rules, into the first one. And I get n equals 48. Okay, nice and simple. From that, I'm ready to go to get my probability that x is equal to 7. And to do that, I'm going to get the Kaz to help me out. So I come down to probability distributions, and I want my binomial probability density function. And for a number of trials of 48 and a probability of success of a quarter, what was the next value for probability that when x is 7? And voila, there's my answer. Nice and simple, huh? What do you reckon? Okay. Now, they don't always get much harder than that, but it's important to be confident in working with mean and variance and practice with some questions. But we do have some other interesting problems working with binomial distribution. What happens if we the number of trials, our n number, needs to obtain, what happens if that is unknown and we have to figure that one out to get some required or desired probability? So the probability of a target shooter hitting the bullseye on any one shot is 0.2. So there's some information there worth noting. Then what is the smallest number of shots the shooter should make to ensure a probability of more than 0.95 of hitting the bullseye at least twice? That's like saying it's like being the shooter and them boasting to everyone, haha, I bet you 95% confidence that I can hit the bullseye at least twice. Well, first off, state our information. Probability of hitting the bullseye or probability of success is 0.2 from the information there. Then I've got this line here. Well, I've grabbed that from more than 0.95. Okay, hitting the bullseye at least twice. So at least twice is the idea that is greater than or equal to 2. Then, where's my information about n? That's what I'm after. What is the smallest number of shots is what I'm after. So first of all, n is unknown, so we can't consider all the values of x greater than 1, because we don't know when to stop. Should be greater than 2 according to the problem. Thank you, Mr. Stevens. We don't know when to stop. We can't go what's the probability x equals 3 or 4 or 5 or 6 and add them all up, because, what is the limit? N is unknown. So this is the first thing we got to do. When x is greater than or equal to is the same as saying 1 minus probability of x is less than 2. This is like the complement of the event. So my expression here becomes this one. And when I rearrange that, I get the probability of x is less than 2 now. Rearrange for probability of x is less than 2. And it is now less than 0.05. Well, see how my inequality signs are swapped around? That's from dividing by the negative here. When I divide by -1, my inequalities swap around. So that's important to remember. We'll swap direction. Okay, now from that, what are my x values that are less than 2? When x equals 0 or when x equals 1. That has to be less than 5%. Now, being binomial distribution, I'm going to put in my rule. My rules for when x is 0 and when x is 1. So there's the first one for unknown n. Unknown n when 0 and my probability of success to the power of 0. And then probability of failure to the power of n minus 0. And because it's minus 0, it's not there. And so on. That's for when x is 1. Now, as you can see, that's not a simple equation that I can solve for by hand, even when it's simplified a little bit. And when I do that on the CAS and simplify it, I entered that in the CAS as I have it written here. CAS gives it to me in a simple form like this. So even still, I don't think I can solve that by hand. And in fact, you can't. It's the type of formula that needs to be solved by CAS. So let's CAS it. Plug it in a solve command like this. Solve this equation that's equal to 0.054n, and we get that. Now, can't have negative trials, so we can forget about that one. Whee! Okay, but we've got this value here. Now we must have a whole number of trials, and we must have a smallest number of shots. And the smallest number of shots that meets this has to be the one that it's closest to. So n equals to 22. And when n is equal to 22, we need our probability to be less than 0.05. Let's check. I'm going to bring up my binomial distribution. That is a binomial CDF, a cumulative distribution function, where my number of trials was 22. My probability of success was 0.2. My lower bound was 0 and my upper bound was 1. And there it is. That's the probability for when x was less than 2. That is, it has to be 0 or 1. And it is less than 5%. Nicely done. And that's it. Thank you very much.